Hi, in this video I'm going to go through the 2024 midterm review for my computational biology class. Now before I do that, I'm going to open up the file directly in my browser by first clicking here and downloading it. And the reason I'm specifying that is it just doesn't work super well when nested inside of Canvas, and so I'd recommend opening it up. When you do that, works even better than if you make it full screen. Let's just make it no teams, so that little bar is not down there at the bottom. And let's just start going through it. So we'll start off at the top left at biology and statistics. First question is asking, what is the signal ultimately used to indicate the nucleotide for a certain cluster in next generation sequencing? So this question is asking, when looking at a next generation sequencing, if you remember, there was a picture in the video I showed during class looking down at the clusters of different DNA fragments resulting from the local amplification of the fragments that originally landed on the flow cell. So they locally amplify so that they're all clones of each other locally, and then that cluster gives off light. A lot of different ways we could refer to that. Specifically, it's a process known as fluorescence. That fluorescence is produced by the stimulation and excitation of electrons via a laser. So fluorescence, really probably the best answer. You know, I also accepted camera, so it's the camera that detects that light. But in the end, that's how it works. One of the interesting things about this is that the signal, the fact that it's given off by all of these fragments that are all the same sequence. The fact is as that process goes on and you incorporate a new nucleotide one at a time, stimulate it with a laser, strip off the blocker, add another nucleotide, stimulate it with the laser, strip off the blocker. As this process goes on, eventually some of the fragments just get out of sync. And that kind of falling out of synchronicity with each other, so that what used to be clonal fragments are no longer perfect clones of each other. This is actually what eventually degrades the signal and causes the flow cell to eventually not be able to produce good sequence data, at least not reliably. And this is why there is, with next generation sequencing, ultimately it's at least one of the reasons why ultimately there is a limit on how long of the sequence reads that are possible. Newer technologies that do long read sequencing don't use that technique. They use a different method of actually doing the sequencing. Next up, we ask, how does read depth data differ from normal distributions and count-based data in general? Well, read depths are discrete values. They're integers. They're positive only, so they're always going to be at least a right of 0, although sometimes you'll actually see 0 included as a count for various different means or reasons, but you'll absolutely never see a negative read depth. That just doesn't make any sense. Additionally, they are discretes. They are integers. They come in units of 1. Now, more specifically, it's not a normal distribution. It kind of visually looks like one a bit, and we often do look at the mean and standard deviation of these values, but in reality, they are very poorly modeled based on a normal distribution. So if you look under my head, it says more complicated models, such as the negative binomial model. These are much better models for how this data actually occurs. And that becomes really important when I need to apply statistics to read depth information, such as in differential expression analyses. That's why I'm often using read depth as a somewhat approachable sequencing concept in this course, is because we're eventually leading into a differential expression analysis project where read depth is the primary statistic that gets analyzed. And to do so, turns out you can't really use just normal distribution. You need to use a fancier, more appropriate model for that type of data. I do actually have another note underneath my head that's just saying that the normal distribution can have a mean of 0 and a standard deviation of 1. These are just common answers I see. But that is a specific normal distribution called the standard normal distribution. It is not a property of normal distributions like as a whole. It's just a specific version. It's what happens if I take a normal distribution, subtract its mean, and divide by the standard deviation. That transformation gives us a standard normal distribution because it makes the mean equal 0 and the standard deviation equal 1, just through that math. Next up, we have major differences between first and second generation sequencing. Well, first generation sequencing was Sanger sequencing. That was one sequence in a pool of liquid that could be the only sequence. And you sequenced it one direction, you sequenced it a different direction using two separate reactions, and then you combine that data to get a pretty good idea up around to about 500 base pairs. I've seen people go further, but it's kind of hard. The chemistry eventually falls off. But in the end, it was one sequence. And if you needed to do more than one sequence, you just had to do lots more reactions. Second generation or next generation sequencing was a insanely more high throughput method because it was no longer one sequence at a time. It was millions of sequences at a time. Sure, you didn't know any of those sequences as well as you did with Sanger sequencing, and the reads were typically shorter, and you had more error rates. But because you could do so many different sequences, you just played with the numbers, and you could just do much more powerful analyses, much faster. So what was the most problematic issue with genome assembly? Kind of in the middle of things. So we had the human genome, reference genome that was made using Sanger sequencing, pretty much. And then around the time we completed that, several years, actually that's not true, a few years later after we completed the Human Genome Project with kind of a rough version of the human genome, next generation sequencing came out and allowed us to sequence all of it, but it still had a pretty big limiting factor, and that was the length of the read. What long read sequencing specifically has allowed us to overcome is that there are simply regions of the human genome that are problematic to sequence, and they're larger than the actual reads. And so until we had a technique that would allow us to read a larger fragment than those problematic regions, such as like the telomere, centromere, and various structural regions and regions not constrained by like protein coding sequences. Once we had reads longer than those regions, it allowed us to really overcome that and produce kind of the most a fully characterized sequence, at least in terms of the nucleotide sequence. It does turn out there's other features that we're still working on the technology to deeply characterize. So that's going to include things like epigenetic changes and folding and things like that. Now, we collectively refer to regions like this as repetitive sequences, and maybe just low complexity sequences will be some other terms you see. But repetitive sequences are by far the most common issues, such as the telomeres, which are just a short pattern repeated over and over and over for thousands of base pairs. Well, our short reads were much shorter than thousands of base pairs, but nowadays we can get even up to millions of base pairs, although that's usually more of a flex. It's not really needed for the most part. You really just need to be bigger than the difficult to sequence regions. Okay, now this one's a little bit hard to see, and really the more important part is this concept right here. Okay, going down. All right, so I could have just moved my picture, but I just sunk down. I'm going to get closer to my mic. Okay, so right here, right there. This is really what I want you to learn. I don't care about this formula right here. You can look up this formula. It's not a terribly easy to apply formula, and because it's because this read word, The word read is often hard to interpret. Sometimes people are going to refer to each end of a paired end sequence to be a separate read. Sometimes they're referring to that as a single fragment of DNA, and so they're going to be calling it a certain read. Really needs you to clarify. And I will say that this is true even within like professional realms. Like you can go onto UT Sequencing Center's website, and I bet they frequently get questions of, now you say fragments, what does that actually entail for a paired end read? Is that 200 base pairs in total, or is it so for 500 reads, is that 200 base pairs in total per read? Or is that 500, 100, and then 500 on the other side? So really, you just kind of need to get that clarified. In this situation, that is what I was trying to describe, that I have 500 reads of a paired end fragment. So really maybe 500 fragment reads, with each one being 200 base pairs in length. But in the end, and this is why I say focus on this formula. I think my words got away from me there. So I'm just going to, again, direct you towards this conceptual formula, which is much more improved, I think, over this like classical formula here. If you simply calculate the total number of nucleotides of sequencing data, whatever that is, and clarify where needed, and then divide that by the total nucleotides in the sequencing target, so in this case, 10,000 base pair, you get the math right. So if I assume that this is correct, and again, if you're not sure, just get it clarified. In real life, it's worth an email to just clarify what this value is. But I get 100,000 total nucleotides. That's being spread out across 10,000 possible nucleotides. And so on average, assuming that every position has an equal chance, I'm going to have an average of 10 observations per nucleotide. And that's it. So, I mean, really, it's a very, very simple formula. The hard part is just interpreting how people are describing it. And that's just, communication is hard. So get that clarified IRL. Next up, we have what's that data structure and order of operations. I wish I would like do some silhouettes so I could actually make this like a Pokemon reference other than just what's that data structure, but one day. So what's this data structure? I don't know about you. That's a little hard for me to see. Better. All right, well, hopefully you can see that, but basically, there we go. That's working. Basically, you have this output. I'm asking you to interact with, or not interact with, but like interpret what you're looking at. Well, what you're looking at is the output of the head function on iris and the structure function on iris. Now, first of all, at this point of the class, I've used this as an example so many times. I hope you recognize that iris is a data frame. But specifically, when I'm looking at this, I can already tell it's a data frame just from this first picture. Now, there are some subtleties in there I wouldn't really expect you to memorize that are clarified in this bottom section. But strictly speaking, I know what a data frame looks like when it prints out. But first of all, I can tell it's not a vector. It's clearly some sort of two-dimensional data, because when I call the head, I can see rows and columns. I can also see that there are numbers mixed in with some letters. So either this is a character matrix, but I happen to know that a character matrix prints off with quotation marks, or it's a factor matrix. But if that's the case, then making like measurements like sepal length a factor is kind of weird. But that said, technically this could look like the head, although I think you would still see a levels printout at the bottom, even if you were just calling the head of some factor data. So I think in theory, I would personally know this as a data frame, or feel very confident at least it's a data frame just from the head. But I also provided the structure. And the reason I provided the structure is because one of the things we can see when we call the structure is that it's got multiple columns that have different types of data. And that absolutely rules out matrix, because a matrix has to be a single type of data. Because what a matrix really is just one big long vector that's kind of wrapped up into rows and columns. In fact, it's stored in memory as a single chunk of data, which has a single type, and it's just stored as a series of positions. A list type object, like a data frame, is not. It's stored in memory as a series of containers. So like container 1, which corresponds to column 1, container 2, column 2, 3, 4, and 5, which they can all have different properties. They can all have different types. In this case, it's several numeric containers, and then finally a factor container. And so that is why this ends up definitely being a data frame just from this picture. In summary, though, data frames can have more than one type of data inside of its, one sec, I gotta fix my picture, inside of its columns, whereas a matrix can't. Also, a two-dimensional data set, there's a number of them, but we've really only talked about matrices and data frames. So just seeing it in 2 dimensions made you eliminate most choices. Finally, you needed to know that if I'm asking for class, if it is a data frame, the answer is going to be data frame. If I had asked for type of, then the answer would be list, because that is the way that a data frame is stored in memory. Okay, so here I am demonstrating an extraction. I say iris by itself is a data frame. I'm then extracting 2 columns and 10 rows from iris. One thing to note is that anytime I extract multiple columns, so because more than one column was extracted, anytime I extract more than one column from a data frame, because of that underlying list structure, R doesn't like simplify it. It's going to remain a data frame because it's consisting of 2 containers. Sure, it's a subset of the size of the original container, so it's actually had to spin off 2 new containers stored in different locations in memory, and they're shorter, so they're just smaller containers than the original iris, but they're still separate containers. It's not going to feel like it can safely simplify this in any way, so it doesn't. This should be contrasted to what would happen if, let's say, I had only done column 2. So if I had left off 1 and the colon and only extracted column 2, because it's simplifying to a single container using that square bracket method, R does take it upon itself to simplify to a vector. And I mean, I can see the argument. It is, in theory, going to be a vector because it is the contents of a single column. However, it's not my favorite behavior, but it is something R does. So you just kind of need to memorize this. So if I'm using this 2-dimensional single square bracket tool and simplifying it to a single column, R does, by default, simplify it to a vector instead of a data frame. Curious enough. Next question. Please put the following in order of execution, then I give you some clarification on what's going on. Now give me 1 sec. My dog is freaking out, and I'm going to go take care of her. And we're back. All right, so in this question, we have a series of functions. We have this object, not a function, being assigned data is a function from the mean function following the analysis over here. Now, there's a few things to note is I've specifically pointed out that several of these symbols are actually functions. And that is just how R works, is a lot of symbols have special meaning. Now, in this particular case, what you can kind of do is just go through kind of the logical order of operations, although I do want to stress, I understand this logic is challenging. But that's why we're here. So let's go through it. Try to make it a little bit bigger for you. All right. So I can't do this assignment until I know what data to assign. It just doesn't make sense. I can't do mean until I know what data to analyze. I can't extract data from empty cars until I know what data to extract. I can't compare the number 1 to something until I know what data to compare it to. So ultimately, the first thing that's going to need to to run is this extraction of mtcars $VS, which is going to extract a column of data. I'm then going to have to run this comparison of that, what on the left-hand side is currently a series of values, and compare it to the number 1. This is probably a little bit tricky, but this is all one big step. Once the equals equals has finished, at that point, that is a single two-dimensional extraction that is simultaneously subsetting the rows based on this logical object resulting from the highlighted code, as well as subsetting to a single column of MPG from the mtcars. This is going to return a vector ultimately. This vector that results from the code I've currently highlighted is then analyzed using the mean function. The resulting length 1 numeric vector resulting from the mean function is then assigned to average STR engine miles per gallon. Straight, that's what it is. Average straight engine miles per gallon. That's what VS stands for, is the shape of the engine. I didn't know that. I had to look that up. But that's how that would work out. Now, how is that working? Okay, there we go. All right. Next up, provide code that calculates the number of falses in object 1. Well, there's a lot of ways you can do this. The big trick is to realize that a logical vector gets coerced when doing math into ones and zeros. So trues would become ones, falses would become zeros. That means if I try to do something like sum, I'm going to calculate the numbers of trues. And so probably the most straightforward and the answer I would actually use personally is I would negate the logic, making the trues false and the falses true, and then just call sum on that. So that's personally what I would do. If I wanted to just see both, I could call table. If I then wanted to subset it to just the results that are false, I could actually extract using a name. That does work. And then there's a lot of other like fancier ways of doing it. This one being kind of obnoxiously complex, but more just to show you the flexibility and how we might do different things. And also just because I like to point out that the mean of a logical vector is the proportion of values that are true. So if I get 1 minus that mean, that's the proportion of values that are false. If I then multiply that by the length, I get the number of values that were false. Just kind of some fun examples, that's all. A lot of different possible answers though. And I really like this question. I think this is a good test of your understanding of what's going on. But here we go. So here I say, what is the class of each object? And that stuff below. We can see letters 1 through 4. Well, letters is a character vector, which means object 1 will be a character vector. I'm then making a data frame. Well, so object 2 will be a data frame, but I'm making it with 2 containers inside. The first container named lower is going to be assigned the values A, B, C, and D. The second container is going to be named position, and it will be assigned the integers 1, 2, 3, and 4. That's it. So it'll be a data frame consisting of 2 containers, one being character and one being integer. If I then open up object 2 and extract the contents of the POS column, that is going to return the data inside. That is the job of a $sign. It opens up a single container in a list type object. Well, that is containing integer data, and so object 3 would return integer. Object 2 then being extracted across rows 2 through 3, so 2 and 3, and then columns all. That's what blank in the after a comma or before a comma means inside of the square bracket tool. So across all columns means that it's going to remain a data frame. And so object 4 is a data frame. And I want you to contrast that to this one at the bottom. Sorry, you haven't seen my cursor for a bit. This one at the bottom where I am extracting rows 2 and 3 and then extracting column 1 in that single two-dimensional extraction. They both were two-dimensional extractions for the record. It's just this one didn't subset the columns, but this one did. In this one, it ends up returning a vector. And the reason why is that just because of the way square bracket tool works in R, if I narrow it down to a single column, it will return a vector, at least when I'm doing a two-dimensional extraction. Thank you, Kira. Okay, so hopefully that made sense. All right, starting up with extractions. Make my picture nice and neat. Make my head go away. That's not my head, that's my head. Bye-bye. Just make me smaller. Whee! Hello, I'm Nolan. All right. That was much weirder at the end. Oh, I'm so tiny. It's really cute. All right, it was a little bigger. That's better. All right, cool. Conceptually describe the answer. It's a little early when I'm doing this. Describe the answer and tell me where the data is coming from. So I am extracting rows 1 through 10 across columns 2 through 3. But then I'm doing a second extraction. Now, this is a silly example. This is not something I normally do. I would normally have just said comma 2, but it's an example just to see if you're understanding things. Once that extraction has taken place, this first two-dimensional extraction, a second two-dimensional extraction takes place. It needs to be 2 dimensions because I had extracted 2 columns, meaning I had returned a data frame. So this had to be a 2-dimensional extraction. In the second 2-dimensional extraction, I'm extracting only the first column, which corresponds to the second column originally. So what I am ultimately extracting are the first 10 values from the second column of iris. Like if I was going in and circling where that data was ultimately going to be returned from, it was from that second column. Maybe a good question example. I should add that to the exam. Okay, so this one is silly. But if you go through this, letters contains your capital letters, the fifth one being E. Then letters is the lowercase letters, this one being X, T, R, A, C, chuns. And then if you check that very end, it turns out to be a plural. And so it's extractions. Thank you, Kat. The collapse is simply sticking them together. This would be a question maybe on the exam if it was more about like you reading documentation and understanding what collapse does. Thank you, Kira. She really likes it when I make these videos. She gets all the attention. Thank you. Yeah. Okay. Let's move forward. All right, write code that prints the rows of empty cars where both are true. The versus column is 1, so that means you'll need to extract the versus column and then say equals equals 1. That's it. Then the HP column, so you need to extract the HP column, is less than 100. Less than symbol, 100. Pretty straightforward. Really, I think the biggest trick is both are true. That means they need to then be joined. So you create logic on the left, you create logic on the right, you join them together with an ampersand. If you had additional things that needed to be true, you could keep on stringing together more ampersands. As long as they were all the same length, it would work out correctly. In the end, you would then need to use that to do an extraction. And that's what you're seeing here. Because this is subsetting the rows, it belongs in the rows section of the square bracket tool. Please note, because I've left this blank on the right side of the comma, that is going to extract all columns. And note, no, I do not need a space there. Just simply having the comma makes that a two-dimensional extraction. And it means that I'm going to return all of the columns. Next question. Oh, Kira. Do you want to see her? Hi, sweetie. It's just hard to get through my background removal tool. Hey, Kira. Yeah. Sorry. That was it. You got her little eyes in the dark. All right. Let's do this next one. Please don't knock that over. So we have how many extractions are taking place. Well, if I want to list them in order, The first one to occur is this extraction of sepal length the first time. I then compare that to 4.5. That's not an extraction, but I then use that comparison in a single extraction and a two-dimensional extraction to extract from iris. I then take that output data frame, which contains the first two columns of iris across a subset of the rows. I then extract a single column, so there is our third extraction, and return its contents. So that is going to be, I think that's the first column ultimately. So right now I have a subset of the values in the first column in the highlighted code. Well, that turns out to be a vector. And the reason why is it's the contents of a container, which is always going to be a vector in a data frame. And so from that vector, I have to do a one-dimensional extraction, which is what you're seeing here. Please note, no commas, because that the data it's extracting from is one-dimensional. So that is appropriate. They match, it works, and I get the first three values from that subset of data. That's it. So 1, 2, 3, 4. I thought that was actually a pretty good practice question. Like, are you really understanding how these can be chained together, why they work the way they are? The biggest mistake I was seeing is people considering this to be like, assuming this is already run, considering this to then be two extractions because like dimension 1 and dimension 2. Dimension 1 contained an extraction, but most people had already counted that one. So then 1, 2, 3, and then 4. Just can't see it. It's under my body. All right, next question. Question 10, write code that returns a data frame with all columns across, just cutting off. There we are. Across the rows of iris where the petal length or petal width are greater than 6.6 or 2.4 respectively. I then provide you like a little diagram of what that looks like. But in the end, the actual comparison is pretty straightforward. You get the data, you extract the data you need. So iris $ petal length, you make the comparison, done. And then there's an or symbol because I'm saying that this should be true or this other comparison should be true. I then use all of that logic, that resulting logical object, that is length 150 because that's how many rows iris has, and use that logic to control an extraction. Nice and simple. Very similar to that ampersand question from before. The difference being here, I want when one of these is true. So like when trying to explore the outside edges of this distribution, not this corner where both would be true. And in fact, no values are here. Right now, had there been any values there, I would have picked them. But I didn't want only where both were true. I wanted where at least one of these were true. Next up is logic and functions. That's cut off a little bit. Wish it wasn't. There we are. So you can't see a final curly bracket, but assume there's a final curly bracket here. I'm not really sure why it's getting cut off. I can almost get it viewable. There we are. Okay, so we've got x equals, I'm gonna make that bigger. I can barely see it. Okay, x equals 1, y equals 2, and then we're doing some logic on that. So does y equal x? No, that would be false. And so this will not run because this was false. Else, if x is greater than y, well, that's not, so that also returns false. So finally, we're going to print 3. That's it. Let's play with this. The question's asking, why does this produce an error? This was a hard one to kind of respond to in class, but I think the actual answer is pretty understandable if you just try to do it. So like, let's just say x is this value, so 1, 2, 3. Y is 3, 2, 1. If I then say x equals y, that's going to become false, true, false. Check to understand why. So then you have to ask yourself, should it print 1 or not? Well, there's 3 different values. Should it print 1? So, or should it print 2, 1, 3? It would be very challenging, right? So somehow you'd need to like loop through each value and try each of these values one at a time. And in fact, that's why it produces, I think, a warning right now, and it ends up just using the first value, which is not my favorite thing, but it's just such a common problem. In the end, the warning message it produces, or the error message it produces, is going to tell you that you should have sent it a length 1 logical vector. And that's the main issue, is that it's expecting a single decision point. True or false? Should it or should it not run the code inside? And that's the issue. If you wanted to go through these, probably some sort of loop would be the general way I go through it. All right, let's zoom back out. Whee. Next up, we have what are the 3, not a typo, values printed to the console in the following code. So in this code, we have a function. When I run that function, nothing is printed. And that's because what a function is doing is it is storing a process inside of an object. It's also allowing you to control what the arguments that you send to the function are and what their default values are, if any. I know, you're very cute. She's squeaking at me. Okay, so when I run this, XYZ 18, well, 18 is going to become X. Y has not been set by the user, so it's going to use its default value. Z has not been set by the user, so it's going to use its default value. So that is going to become 18 minus 3, so 15 divided by 5. So in other words, that is then going to create an object inside the function. I'm never going to see out, but it's going to create an object called out inside the function that contains the value, what, 3? Yeah, 3. Because that was 15 divided by 5. It's then going to return the value inside of out. So it's going to return to the user 3. And what's really key here is that the user has not assigned that data to anything. That means that at least for most objects and your common numbers and characters and things, all the stuff we're used to seeing are going to follow this pattern, the default value is just to print it. So if it doesn't get assigned, it's just going to get printed and then it goes away, never to be seen again until I rerun the code. So that's going to print 3 by itself. This is going to make X 12 and Y 2, not because Y was 3 before or anything, but because these are 2 unnamed arguments. And so they get applied in order based on like what spots in the argument list are left. Well, none of them have been set by the user, and so X and Y are the first 2. So that becomes 12 minus 2, so 10 divided by 5, so 5. Nope, 2, sorry. Out is therefore 2. That data gets returned to the user, and I still haven't assigned it, so this time it is going to print off 2 as well. So we printed off 3 the first time, 2 the second time. The third time, we could go through the math, but in the end, it's not going to print anything out. So nothing is going to be printed because I have literally created an object from the output of that function. I did happen to name it out, so that will create an object called out, but from the inside, it's the reason the name is whatever I've named it on the outside, not because its original name was out. That said, I do want to run through how that function would work. Z would be set to 2, and then 5 is going to be sent to the X argument since it remains unset at that point. So Z would become 2, so this will become 5. Y is going to use its default value, so 5 minus 3 is going to be 2, and then I'm going to divide that by 2, so that's going to that's going to return 1, but that 1 is going to be stored inside of out, so it does not get printed. Last example, z set to 2. I then set a second argument, again unnamed. Because of the order of arguments, it's going to go to x, which has not been set by the user yet. And so that is going to become 13 minus 3, which is 10 divided by 2, so that's going to return 5. Some good function practice. Definitely be able to just go through that one, kind of understand all of those little subtleties. Let's move forward. Okay, I like this question. I think maybe it was a bit much for the class, but let's go through it. It's not too bad once you get it. So here we have a function being made, and I'm going to ask what is being printed. Well, when this function runs, nothing is printed. I know it's got a lot of print functions, but these are like instructions. It's not actually printing whenever I run all of this code. It's storing this process inside this object. There's a difference. It's like the difference between me giving you a recipe and you making a cake. Whenever you use the function, you're making the cake. When I hand you the function, that's you or when you hand R the recipe, that's you giving it the function itself. That's the difference. And then coming down here, you're so funny. Coming down here, again, our bottom curly bracket's getting cut off, but I can make it up here. Coming down here, I then create an object called x that's never used again, purely there as a distractor. Sorry, it was a 7-point question. I was just trying to mess with you. Never used again, doesn't matter. Is.logical. Is.logical is going to test if the question object is logical. It's not, it's a function, which is not logical type of data. It's a function type of data, I think. It may actually have a different name, but it's classes function for sure. But it's definitely not logical. So that's going to return false, which means this is the line of code that will run. Now at this point, I need to go back up to the function, and I need to set the internal argument 1, whatever its first argument is, to the value 2. So let's do that. Forgot to scroll up. Okay, there we go. It's pretty legible. All right, so its default argument, or sorry, its only argument does have a default value, but that default value doesn't matter. The user always wins, and so x is 2. Okay, so if x is 2, based on that code down below, this returns false, so this doesn't happen. X is 2, so that returns true, which means this does happen, and then we exit the chain of logic, so this does not get printed. Finally, I return the value x, so the value of x is 2, so 2 is going to be sent back to the user. In order to determine whether or not it's printed, we need to go see what the user is doing with that sent back data. And it turns out that the user did not specify what to do with it. Something I've said a couple times in this video now is that unassigned data is going to be printed. Like that's just most of the time, if I have unassigned data, what happens is that data gets printed. And that's precisely what will happen here. So in total, we would end up printing off function, and then because it was unassigned data, the returned value of 2. So I think this question is fun. I get a little snarky in it, but basically you just need to remember a tiny amount of your statistics and then try to apply the function. Now this is going to be easiest for me to just demonstrate using R. So if I make the function, I can then try to use it. Let's just come down here. Let's say I want to do what is the displacement after 1 second at an initial velocity of 25 and an acceleration of -10 meters per second squared. Well, at that time, the value is 2. I did say I've constrained the time to integers, so you could literally just sit there. Well, after 3 seconds, that's at the same height. At 4 seconds, it's falling back down. And hey, there we go. At 5 seconds, it's back to position 0. So that's really all you needed to do to find that first answer of when the object going up and then coming back down would reach a displacement of 0 is just figure out how to read this. Remember that displacement of 0 means it's returned to the original position. If you then wanted to test out what was its position at halfway through that, which is at its highest point, well, that would just be at half point in time, so 2.5. And so we can determine the displacement. If I really wanted to, I could even plot this out. So I could say, I don't know, let's just make a vector. So I'll do 0 through 500 divided by 100. Let's check that math. Okay, so that's going up to 5 seconds. Let's do through 600, just for fun. Okay, so we're going to plot out all of this data. So we'll make the x-axis time, and then we'll calculate the displacement as a function of time. And I got to end my plot function. And there we go. With that, we can see our lovely little parabola. And what's happening is I'm plotting the x-axis. I'm then using this calculation and plotting its displacement. So basically, I've just used this as a graphing calculator. Nice and easy. And you would be surprised how often just like simple algebra and calculus comes up like that. And or technically calculus, although it's not like you're going in between that and the next derivative or integral. But hey, anyways, let's move forward. I just like that question. This next one is saying that you have got a pattern. I eventually want an E followed by an M, and I want it to be flexible. So I should have probably said that a little bit better. I'll need to reword this for next year. But I want an E followed by an M, such as in lorem or in eusmod. So in order to do that, it needs to be able to be 1 or 0 or more characters apart. Well, there is a pattern that we've kind of learned that allows us to do that, and that is a combination of 2 different special characters. Yeah, I'm just going to make this small. So sorry, zoom in if you can. I'll move my head out of the way. Ooh, I'll just come over here. Hello. It's going to be a problem. Next question. Yeah, there we go. It's beautiful. All right. So in this question, I want it to be an E followed by 0 or more characters, eventually followed by an M. And so a dot and then an asterisk is a way of combining any character with 0 or more times. And then finally an M. Now, for the record, by default, this is going to grep the longest possible match. But for grep, that doesn't really matter. I'm not doing gsub where I'm taking that match and then like replacing it with anything. Here I'm just saying, is there a match or not? So basically searching. I'm searching for a pattern. If there is a match, then it returns the position. That's what grep does. It returns the positions that contain any matches. I did say here that a plus would work for eusmod, but it would not work for lorem because lorem does not have a additional character between E and M. It has 0. And plus only works if you have 1 or more characters of the preceding value. Which, just for the record, the dot is any character. The asterisk modifies the preceding character, which in this case is the dot. Could have been a lot of other things, though. Next up is a very similar question, but this time I'm looking for return all values that begin with an S or end with an M. So for that, you need to know the symbols caret, and you need to know the symbol $. Caret stands for the beginning, $sign stands for the end, and then I've joined those patterns together with a pipe, which just literally gives multiple patterns to which with to make a match. So if either one of these is true for that string of text, it will return that it is a match. And so to make lorem work, we need to include this $. To make sit a match, we needed to include this one. And so that works out. If they had two matches, so if it began with an S and ended with an M, it would still just return one position. This next one, it's not my favorite. My example doesn't work quite well, but let's get into it. So in this case, I'm looking for an a P followed by an I. And I need to make this a bit smaller for you to see. There we are. A P followed by an I, and it should be replaced with a $, an exclamation point, exclamation point, exclamation point. So here, this is why I said it's not a terribly good example, because my P and I were already right next to each other. So strictly speaking, since I didn't technically make it like required to be separated, you could have just said PI and then replace it with exclamation point, exclamation, exclamation point. Although strictly speaking, I did imply that it should be flexible because I described what's known as a lazy behavior up in the second bullet point. I say, in the event there is more than one I followed by a P, the match should stop at the first I. Now, that's not actually what I describe in my answer down here. So actually, I'm going to have to go back and edit this a little bit. But what my pattern is doing is if I have a P followed by any character 0 or more times, followed by an I, it's going to make a match. And then because this question mark is here, modifying my modifier, my asterisk, it's going to make that match short as soon as a complete match is found. And so if I had multiple options for P and I to be like found next to each other, it's going to select the shorter one. So for example, here, it's going to choose this shorter match rather than this longer match. But I think I would need to reword this so that it was said in the event that there is more than one I following the P at any point, the match should stop at the first I, not if there is like multiple I's next to each other. Although what I've done here would still end up working for that particular scenario as well. The important part from that is the lazy operator that is going to stop at the first match. Next up, the following returns a vector or data frame. Well, I am extracting from a subset of rows across all columns. So that's going to return a data frame. It is going to extract based on the row section. I can tell that because my logic object is inside of the row section, so it's going to be rows, where both or at least one of the following, so here I can see that my two pattern searching and value comparison logic objects are being joined together with an ampersand. Because they're being joined together with an ampersand, it means that both need to be true to return that row. Finally, you just need to interpret this grepl. This grepl is going to return logic. That's what grep with logic does. It is going to return anytime the first character which can be anything, is followed by a lowercase e. So this is literally the beginning of the string. This is any character, so that's together the first character, and then followed by a lowercase e. So that is going to return true only where that is present, and then it's going to return false if that's not present in that value. This is just a standard numerical comparison of less than or equal to 2.3. In summary, I'd probably say just an E following the first letter, or less than or equal to 2.3 for those blanks. And last question. Last question is correct the following so that it produces the following output. So to do this one, we're going to need to pull up the RStudio just so that we can play with this code a little bit. We should be able to read through mostly what this is doing. It's obviously calculating the Fibonacci sequence. So Fibonacci, why did I even think I could spell that in front of him? That might be right. Don't judge me though, if not. Here I'm creating an object called FibLength. I don't really describe what, although I do show here that it's used in the length 3 through FibLength. Let's come back to that concept. I then use FibLength here to create a vector of missing values. Okay, so that would mean this needs to be a number. It's presumably, well, no, it's not presumably, it's how long this object is. I'm then doing something to that object, probably an extraction, and assigning it the value 1. Okay. Working through here, I can see that here I am extracting something from fibvec, okay, and assigning it something from fibvec plus something from fibvec. Well, if you're not familiar with the Fibonacci sequence, the idea is that you take the previous position, so say if I'm looping through the positions I minus 1, combine it with the second to previous value, and then you literally add those together to create the current value. If I'm starting from 3 through the length of that object, then that would work out because the first two values should be 1. Well, if that's true, then that must be what this was doing. This was creating known values at the second and first position. So that is how that would work. Finally, we could just create some test code. I'm going to put in a value I know to be not the right value. Let's just do 5. This is then going to create a vector of 5 and A's. This is then going to replace those first two values with 1 and 1. This is then going to create a vector of 3, 4, and 5. And so I is going to become 3 the first time, 4 the second time, and 5 the third time. Finally, it is going to extract those values each time, adding them together. So for example, when I equaled 5, it made this value here by taking the I minus 1, so the fourth value, and adding in the I minus 2, so the second value. So 2 plus 3 is 5. If I make that larger and repeat the process, I get 8 because that was 3 plus 5. If I make that 7, 13, and if I go back to the question, I can see it ended at 55, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I make that length 10, we get the same answer. So in the end, I have correctly remade that object, or that piece of code. And that's it. Definitely probably the hardest question in here. I need to make that a little bit easier for the game next year. Nobody actually asked that question, so I probably would have given you a hint. I probably would have just told you fib length. to be honest. But anyways, I hope that helps. I think that is the end. Yep, that is the end. If you have any remaining questions, please just post questions into Slack. I'm also going to have a tutorial later tonight. So good luck studying, and let us know if you have any questions.